Está bien? Oh. And how does the screen sharing work? Ah, perfect. Hi, welcome to our next challenge or our next topic we want to speak to. It's about CK, but before we're going to start with that, I just want to chill quickly our Speedrunners event on Thursday night. We have kind of organized a bar with some free beers, some free drinks, and would be happy if some of you were going to join. So you have also the chance to talk the BuidlGuild crew, the BuidlGuild team, and yeah, met us all in person. I think that's our first time that we're doing something like that, so it would be very nice if you would come. Here's kind of our QR code. So if you want to, if you want to scan it, then you will find a link to our Luma event and sign up for that. Okay, but how do you? I don't know how this works. Okay, but it's okay. Okay, let's start with the seeker. So I'm Philip from the BuidlGuild. I'm happy to have all here. I had the honor of the last couple of weeks to go a little bit deeper into the Seeker route and see what kind of apps we can build with it. I mean, we have all these mathematics about CK, very complicated stuff, but what actually you could do with it. And yeah, and that's how the CK voting app came up with. And the next hour, I just want to walk you through the CK voting app, all the basic concepts, how it is done, and then in the end, leave you out of the room that you can build your own app. That will be my goal for today. But first things first, who of you have built a CK app so far? One person? Okay, not so many, so it's two persons. Nice. So the workshop is perfect for you. And what about who of you have kind of voted in some on-chain proposal or some voting or whatever? Yeah. Quite a ton, and this is kind of what happened also to me, because the thing is, when you vote on-chain and anyone kind of knows your address, all the votes you're doing are just out there in the public, and everybody knows on which proposal you voted at. And that's exactly why we're here today. So kind of the presentation is kind of split. I walk you through some things. First, we're going to touch some how mixers work. That's kind of like Tornado Cash and how these things are done. Then we need to touch on a very important concept. Maybe for you, sometimes it's Merkel trees, but it's a special version of a Merkel tree. It's a Lean Incremental Merkel Tree. Then we're going into the CK circuits with Noir, what sounds very fancy and very complicated, but actually it isn't. So it's pretty cool to see that and how we can get a very nice Solidity Verifier, very easy out of that. And then in the end, all kind of how we're putting everything together. But so first, let's go with the mixer part. And the thing is everything is kind of on a blockchain is transparent. I mean, that's very good in some sense, because it's just very transparent and it's just no trust needed, huh? Because you can see where your funds go, how many funds are in a protocol, in a smart contract. This is just open to the public, and so nobody really can scam you, because you know exactly where the money flows. Of course, they can take it away, but you see at which address then has the money. So it's completely different than in the banking system. But the issue is also for you. Imagine it's me, I'm gonna get paid some salary on an address, Ethereum address that I own. And my employer already knows that address, so they send the fund to that, and what I'm going to do now? So these people in the company know my address, and if I even send it to another address, the employee can just look into Etherscan, see the transfer, and see it, okay, the account, the new account. So I really cannot, all my wealth, everything I have on-chain is kind of public as soon as anyone knows the address. So they see all transactions, they see kind of the balances of all ERC20 tokens, just everything open. And I mean, that's an issue, especially for me. And also all kind of other things you do on-chain. It's not only sending money, you can also call functions in some smart contracts, you're playing games, whatever. Everything is just open. And that's kind of a huge issue. And so the main issue really is, how do you kind of break this connection between one address, it's kind of the sender address, and the receiver address. And in this case, there's one way, and that's kind of mixers. So that's kind of like a mixer in a basic concept. So you have, on the one side, you have kind of many people, they come all together, and they kind of deposit something or put a secret into kind of a mixer, so all in the pool together. And then in the end, it happens, that's kind of the last step, they withdraw or gonna do something out of the pool. But the thing is, everything in the mixer gets mixed, so there's no connection anymore from the one group who started to the other group. You only know, okay, that were the people, but you don't know what each individual in there has done. And this is kind of the concept of a mixer. And like I said, it has 3 phases. So the first phase is the deposit phase. And here, we kind of have a user, that's you, that's me, kind of. We're gonna generate some kind of secret. And this is only known to us. So we keep the secret. This is like we should never have it out. It's a little bit like our private key for any wallet. And this secret kind of gets hashed into a commitment. So this commitment gets on-chain, and I could pair it in this sense with some ETH together. And these go into the mixer. And the secret stays with me. So I can at some point prove, because I have the secret, I can hash it, and I can say, okay, I have the commitment to that one. And in the second phase, many more users doing that, and they all putting their ETH into one pot. So actually, there's just a huge pond where everyone throws in their ETH, and in the end, everybody thinks, okay, that's my ETH, and that's my ETH, and that's my ETH, but in the end, nobody knows whose ETH is what. So that's kind of the whole thing. And the only thing what you have kind of a node somehow. You created before, and this node can then prove that you are an owner of one of these ETH. But all these ETH in there are kind of the same. So how is it done? I'm the user, I'm using a complete different account, so it's important that it's not my account address, because if I would use again my same account address, everyone knows that's me, so using a different address, I somehow have a secret. With the secret I prove in the background to the smart contract that I can pass the gate in case this dog, and I can take my ETH out. That's kind of the basic concept of a mixer. And here I gave the example with some ETH, but you could also use the gate instead of the ETH withdraw. You can call whatever function could sit here in the back, whatever you want. And in this case, for our voting app, it's the vote function. But we will see that later in a little bit. So that's kind of the basic idea of how a mixer works. One important thing about it, because I was talking about, if you imagine you have this whole group here on the left side. Of course, if we would imagine in the extreme case, there's only one person using this protocol. I mean, this whole privacy wouldn't make sense, because there would be here one person, put something in, what should be get mixed? There is only one ETH in there, and I take it out. Of course, everybody would know that's me. So it's very important. The bigger you're getting this size on this side, the better is your privacy. Because imagine if you have 2 people, you still need, okay, maybe these 2 people, but if it's 10 people, it's 1,000 people, it's 100,000 people, the privacy just kind of grows. And now an important thing here to know is, we came with the example of one fixed denomination, one ETH. Here I put the example, if you would go with some weird number, I'm gonna put in there 0.378 ETH. And in the end, to a later point, I will withdraw 3.78 ETH. It's kind of very obvious who this person is. Huh? Everyone else puts 1 ETH, and I'm one person who puts that ETH in. And then everybody would know, okay, the new address, that's exactly that address to put it in, and you have immediately a link again, so the connection is not really broken. And that's why you have in these protocols, I mean, there are some ways you have a fixed denomination. So if you look, for instance, for some privacy pools or Tornado Cash, they have one pool with 1 ETH, another pool with 5 ETH, and then the other ETH, a pool with 10 ETH. And that's kind of, is it done? I mean, there are the other things. I don't want to get into nuances right now. You can also use some UTXO, and then you split it up, and then you cannot mix it anymore again. That's like newer things. But this is the core thing. And actually to say the bigger the people are, you have a fixed denomination, the better it is in general. That's kind of the base for our CK voting app. So we're using a mixer, but instead of withdrawing some ETH, we're going to call a function in here. And therefore, I'm going to split it into here in the 2 sides. So we have kind of the back-end side, I just call it back-end on this side, and we have kind of the front-end side. On the back-end side, this is everything that has to do with Solidity and Noir on this side, and getting our Solidity Verifier Contract out, because we need that to plug it in. It's kind of this dog, you can imagine, we have seen. And then on the other side, we have the front end. Normally, in the other speedrun challenges, we're always focusing on Solidity. But here, it's a very important part, the front end, because we need to generate the proof off-chain. on our machine, because this is all secret. It's kind of the private. We don't want to leave that out, because that's us. So we have to touch, in this challenge, also kind of the front end and generate there the proof, so we can later then plug it in and send it to the verifier contract. Okay, first things first, we need to do the registration. That's kind of the first phase we saw in this mixer thing. So somehow we need to put our commitment somewhere that we can later prove that we are part of this whole group. That's what we're going to do first. And therefore, we're going to use a Merkel tree. I don't know. I mean, Merkel tree in the first place sounds very easy. If you go, for me, it's very basic. If you go deeper in it, it gets more complicated. And then if you think about other things like, I don't know, it gets very complicated. So I kind of try to break it a little bit further down. So I don't know, who of you is familiar with Merkel trees and how they work? Yeah, a couple of people. So just for the other ones, I'm just going to summarize it and try to do it quickly before we're going to go then to the incremental Merkel trees and how this is different to a normal Merkel tree. Okay, here on the one side, we have a normal Merkel tree. We have kind of 4 values in that. So that's kind of the registration. So you could say, okay, we have 4 users registered, and the first user has a secret 1, 2, 3, 4. That's kind of the values. Could be hashed things. And this Merkel tree has a depth of 2 now, because we always count from 0, so it's kind of a depth of 2. So we have 3 levels, 0, 1, 2. That's kind of the thing. So when we want to have a new party registering to that Merkel tree, because we need to somehow track the data structure, who has registered, what will happen to this normal Merkel tree is it gets probably very big, much bigger, because we need to add another node. That would be the 5. But we cannot plug it in here because we're looking at that. We're going to create the whole right side of the Merkel tree again. So this one then to calculate, we have to go calculate, we have to increase the depth. This is kind of complicated and put everything on chain. I mean, a normal Merkel tree, for instance, is good when you consider a Ethereum block. You have an Ethereum block, you're getting all the transactions in, and then there is the final state of the block, and then you have the transaction, nothing changes anymore, it gets proposed, and the whole Merkel tree is calculated. But we won't change that Merkel tree anymore. But here, and then it can be there, and then it's good. So for Ethereum blocks, it's very nice to have just a Merkel tree. But to add more to more things, to register our people, that doesn't work, because we have over and over recalculate the whole Merkel tree, and that's kind of very, 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 very cumbersome and just not the best way to do. And that's why there are incremental Merkel trees. And the difference is that we go in and we say, okay, we want to have a certain amount of leaves, that's all these numbers, and we're going to fix the tree already. So it's already there. So as you can see, we have here 8 leaves. That would mean we have place for 8 users that could use our protocol, kinda. But these leaves here are already empty, like before. They're already there. And what we're going to do, we're going to pre-populate them all with zeros, or whatever we want to have. For instance, for tornado, it's tornado, the word tornado, it's hashed, and it's put in here. And now if we're going to put one new value in here, we only have to recalculate the kind of the frontier, is it called. I'm going to explain in a second what that exactly is. And the cool thing about this one, you kind of can track the frontier more or less and put the whole thing on chain, and you always know where you're at. So in this incremental Merkel tree, here you can see now we're going to add the 5. So we're going to put the 5 in, we hash it together with the 0, and we just go up. And this is kind of the frontier I meant. So if we then would populate this one, we do the cell calculation. But the tree itself always stays the same. So it needs to kind of prefix from the beginning. So, and I was talking about that's an important thing about the frontier, how it gets calculated so that we can save the store on chain. And this is exactly how it happens here. So because we say, okay, we have a depth of 3 in the other one, in the Merkel tree we saw before. Just go back quickly here. We have up to level 3, so that's kind of a depth, has 4 levels, more or less. That's why we're starting here, and we're having this little array here in this corner. And now how it happens. So we're going to add the number 1. We're going to get the add number. We're looking at the array and say, okay, the slot is empty, so we can just put it there. So we have the number 1 stored. This is how, when the first user adds it to adds himself to the Merkle tree or the commitment registers for the application, it's here. So the second one adds the 2. Now it comes. Now it gets a little bit complicated because we already have in the first position, we have the number 1. What we're going to do, we're going to use the number 1, hash it together with the number 2. We clear the spot, the slot, and carry it forward to the next one. So we have it stored. Now, only with this little array, we know exactly how the Merkle tree looks like and where we have to add the next value to it. And so on. Number 3, it's very easy because we have the 0, we just put it here. The 4, it gets then a little bit more complicated because we have the 3 is kind of occupied, the 0 slot is occupied, the first slot is occupied. So what we're going to do, we take the 4, we hash it with the 3, we need to go to the next slot is also full here, so we hash these 2 together, and we're going to move it forward to this one. And that's then how our front here, like this kind of this border around would look like, and we know exactly, only storing this array, how our Merkle tree looks like. And you could imagine, when we would extend that to a depth of 16 or whatever, we would have already, I don't know, 60, 70,000, something in between of leaves in there when we have the fixed depth. But then you just have an array with 60 numbers. So it's pretty cool, actually, to track the state of the Merkle tree. And that's what we're using for registering the people. This is very gas efficient, and it also works very good with CK. That's why we're using this incremental Merkle tree in there. Yeah, maybe, okay, I'm kind of switching now from the presentation to the code to show you actually how our code base is set up and how we work then in the different circuits and how we're going to implement it in the Solidity code. So let's go into Cursor. I have already installed everything, and the thing is I have already put in all the solutions in there. So the code is full. If you would do the challenge yourself, you find empty spots like you maybe know it from other challenges in there. So what you can see here, we have another package. Is it big enough to see? No? No? It's better? Okay. I mean, that's kind of the normal scaffold Eve setup. The only thing you can see, we have another folder in here, that's the circuits. Here will everything happen with the Noir in a little bit. Then we have here the hard hat, and then we have the Next.js. Our contract looks pretty easy because, I mean, probably many of you have just a very counter app, a voting app. It's just pretty basic going forward. So if you're going into the voting app, we close all this stuff. I mean, we have the normal the voting app. As you can see, we're using the Lean IMT from here. So a library is integrated, so it's very easy. We don't write this ourselves. We're going to use that from the CK kit. That's a very nice library out there. We're using that one. So then we can initialize more or less the tree here as an empty variable in the beginning. And regarding the functions, so we have kind of, how should I say, for the voting, we doesn't want to let vote everyone, because otherwise we could just create random addresses, let everyone vote, and we had kind of a Sybil attack, our voting attack. We want to make sure that there are only dedicated people can vote. I mean, there are many ways, and the easiest one is just have a allow list. Just send all of my colleagues, just send me their addresses, and I add them to the allow list, and then now these addresses can only vote on this question, for instance. That's the thing. That's why we have the add voters here. And then here we have the register contract, function, sorry, for that. And this is kind of a normal register like we do. And the thing is, as you can see, we have embedded here the tree, and we're gonna inserting the comments that get in from the register function. And this nice library tracks it. So you're going to add that, and everything is kind of calculated already, and they will do the frontier calculation for you. So it's in there, and we're keeping with that track of the whole registration and which are the users who have registered already. And of course, then we're going to emit a leave, and we're going to and we're also going to set the commitments to true if it's the case, and they have registered. That's kind of the thing. I mean, that's pretty straightforward to do that after you have understood how kind of this incremental thing works. Because I think it's pretty important to build the whole thing. So when we do that, kind of the registration effect. Now comes the fun. Now we're gonna jump into Noir. And that's kind of the circuit. So, okay, maybe in the beginning. I mean, there are a couple of words. I mean, I just took them out. I mean, one thing is kind of a zero knowledge proof. Probably everyone of you knows already what it is. It's kind of, you have kind of a secret, and you are the prover with the secret, or whatever you know, and you want to prove to another person, that's kind of the verifier, that you know the secret without revealing the secret. That's exactly what we need to do there. So we know we have the secret, we have the commitment, and we have the secret. We don't want to reveal it, but we have to make somehow sure that the verifier believes that one commitment in the whole Merkle tree belongs to us. That's kind of the most important thing, and that's exactly why we use a zero knowledge proof for that. And then we have, I just pointed out 4 words. They always appear somewhere, and they're a little bit confusing to me, because I didn't know. That's why I mean a circuit. What is a circuit? It always sounds so fancy. In the end, it's just a program you write, kind of in Noir, and that program you use then to create a verifier contract or whatever. It's kind of the set of rules you define something with a proof needs to pass. Then we have the constraints, or the assert function. That's actually in the contract. It's like just a normal assert function that everybody knows you in the circuit itself, in the program. Then we have the witness. And the witness is kind of you could have many inputs in going into a proof, for instance, and using these proofs, these inputs to create the witness. This kind of is a secret to you, but with this witness, you can kind of convince the backend to create a proof that you know these inputs, and out of that comes the proof. So you can imagine you're going to build the circuit, then you're going to get the witness out of it, and with the witness, then you can have the proof out of that. But we're going to see it in a little bit. Yeah, and that's kind of the most important terms, I would say, for general understanding what's going on. Okay. And the next thing I want to talk quickly about is Noir. I mean, I have mentioned it. I don't know how many of you know it already. That's kind of a programming language, kind of adopted from Rust. So it has a Rust base, more or less. It's developed by the AdStack Labs. They're also coming up with the privacy layer and so on. And this one you can use to create all kind of circuits yourself and write them in a very easy way, because it's just a Rust base and not something other fancy. And with that, there comes Nargo. I don't know, that's kind of the cargo, like the CLI tool for Rust, but just for Noir. That's why it's called Nargo. And we have always this Barettenberg. I don't know, in the beginning I was a little bit confused what this Barettenberg is. The Barettenberg, more or less, is the kind of the back end who runs all the difficulties in the back end to create the proof and so on. That's what it does. So you can imagine the Noir writes you the circuits, and you're going to pass then the circuits with the inputs to the Barettenberg. They do some magic, fancy mathematics stuff out, and the proof comes out. Yeah, and maybe, because I mentioned it, let's jump into how a Noir circuit looks like. So I have set it here up. And this is kind of it's a little bit difficult. We will go through step by step to each of the different things, the lines, why they're in there. But it's more or less, like you can see, it looks like Rust, doesn't it? It's just like the normal Rust thing. And what is the important thing here when you're creating these circuits? You're having 2 different types of inputs. So you have public inputs and you have private inputs. The public inputs are visible to everyone. So everyone sees what are the public inputs, and you even need to pass that into the verifier to prove the proof. But there are also these private inputs. And these are kind of the secrets or the things you doesn't want to let know anyone. And as you can see here, it has no color really, huh? Here, all these pub words mean it's public, and if they have no, like these 2 here, they are kind of private. And here comes already the first thing I kind of want to talk to is kind of our secret, because we have the secret together. So we have a hashed of 2 values. It's one time the nullifier and it's the secret. To make it a little bit, because we want to make sure that only one commitment can go onto the Merkle tree. That's why we're going to track the nullifier as well. And we're going to store this nullifier also then in our contract, so that not many people can just over and over and over again vote in the whole thing or create or in there. That's why we're going to store it. And let me go back to the presentation a little bit. So that's kind of maybe the commitment scheme we're having. I mean, that's pretty straightforward. We have the secret, we have the nullifier, we hash it, that's the commitment, and that ends up in here. And like I said before, the secret and the nullifier shouldn't leave your laptop. Another thing with the nullifier is, we also have to we have the nullifier hash. So we don't use the nullifier itself. We want to use the nullifier hash. And maybe it gets a little bit too complicated. I hope I don't confuse you all. Maybe, I don't know, you can give me a quick sign. Is it too fast? Is it too slow? Is it all good? Okay, cool. Because the important thing, and it took me some time to wrap my head around, and hopefully I get it right again, is you need to track the nullifier somehow, like I said, because you want to prevent the double spending stuff. But you also don't want to have, because it's a secret, you don't want to have it out there. So you're going to use the nullifier hash. And inside the circuit, what you want to check, you want to always check against the nullifier hash. So that a user, because you can imagine, you're using your nullifier, you're going into the proof, a valid commitment is kind of computed, and you're passing the proof and everything in there. But if you don't check against the nullifier, you can do the same again, but you just choose a completely random nullifier that is not there and the proof just passes. That's why you want to compute inside the circuit your nullifier and compare it with the public nullifier hash that comes into here. Does it make sense? Probably was a little bit complicated. You can ask me again afterwards. Does it make sense? Okay. Let me go in here. So we have a nullifier hash in here. This is public because you have this in the Solidity contract to track which nullifier got already voted on. So you wanna track that. But the nullifier is kind of a secret. You wanna have it secret away. That's why here you see it's private. This one. So what we're gonna do, the nullifier. The nullifier, but you can see kind of the nullifier hashes. You can kind of see because they're public. But you want to make sure that no one can many more times call the same function. That's why you're going to use the nullifier. You hash it in here, so the person needs to pass in the nullifier, but it's private, and you cannot guess a nullifier. And then you compare the computed nullifier hash with the nullifier hash you have passed in. Okay? Good. Yeah, this is one thing to keep in mind in here. And I mean, it's also pretty easy to calculate a hash. Maybe I have to mention that there are very nice libraries in here you can just use, and you can use from the Poseidon. This is a hash function. This is kind of CatCheck for Ethereum you see many times, but this is kind of made for CK, so it's just more efficient and better to use. And you can have these libraries, and then you're calling in these functions more or less. Yeah. That's the one thing you have to keep in mind. Let me jump this a little bit. I mean, here you can, because you're going to pass in, if you go back in here, in the function, we're going to pass in the siblings. The siblings are kind of the nodes in the Merkle tree. So you always have the siblings. But these siblings need to be private, because as soon as this gets public, you know exactly where you are in the Merkle tree, and you don't want to give up your position, because then everybody knows who puts the commitment in. Because you signed a transaction before, put the commitment somewhere, but you don't want to do that. That's why you have to keep the siblings always private. And to calculate the depth, it's like we have seen in the frontier. You can kind of count. You take out all the zeros because it's a fixed array. We have here a fixed array of 16. You're taking out the zeros, and then you're having the length of the array, and then you know exactly the depth of the Merkle tree. And this one I'm gonna do here. I let compute. There has some advantages, and then we pass it later in, if you go here, into the computed root thing. That's what we kind of do in here. And then there is a little bit weird thing in here, because we need to let the function here, this is the binary Merkle root function that comes from a library I import, similar to the Solidity library, but this is made for Noir. And here we need to let it know which exact index we are at. And if we go up to the inputs, we see we have the index is a field. A field is kind of an integer in that way. It's just the very basic unit you will put in, and whatever you don't know, you put a field in first, kind of. So that's a UN 25.6 in Solidity, more or less. And there's a very nice trick, and that you cast down the number into kind of bits. So you break it. So you break it down. And how this works, also here made a little explanation to that. So when we want to get the index in binary, what we have the index. So let's see, okay, we have number 4. That's kind of our 5th value you put in there. It's a number 4 because we start counting with a 0. That's a 0, 1, 0, 0. Then what we do, we're going to reverse the order, and we pad everything to reach the length of 16 because we predefined that. That's kind of our length of our predefined depth of our Merkel tree in that sense. And then when we want compute now the root in here, we're getting in the siblings from here because we have 0 and 0 and 1, 2, 3, 4. When we go here, we'll be putting the 5. So one sibling is 0. This is the next one. The other 0 is 0, 0. And from this, the sibling is 1, 2, 3, 4. And then we know the depth, and we have the index we just recently calculated. And then we have 2 rules to follow. If it's a 0, we had the hash looks like this. We have it on the left side, the current, what comes in, and the sibling to the right side. And if it's a 1, we have it the opposite around. And this is exactly what they say here. So when we go for the 0, we're going to go over here. We say the current goes to the left, and the sibling here. So we know we need to hash these. Because when you're hashing 2 values, the order matters a lot. So if you change it, it's a completely different hash. So you always need to make sure you really hash in the same order. Yes, that what we kind of do. And when we go now back here to the to our circuit, you see in here that we kind of then asserting. I just gonna sum it up a little bit because that will be taken now probably a little bit longer. Here, the most important assert we do in here is the computed root equals the other root. That we're gonna do. Because we're gonna pass in the root what is the latest root stored in our Solidity contract and compare it to the normal root. If this is correct, then the Merkel tree is good. The Merkel proof is good, and then we're gonna let it go. Otherwise, we just reject it because it's just bullshit what the person said because that doesn't can calculate the tree all the way up because they don't have the right things. This is kind of here it works, and then there is maybe an important thing to mention. As you can see, when we go up here, I see the vote, and it's kind of the question if it's a true or a no you want to vote on. So it's kind of a binary question with a bool we chose, and in here we need to have it in here because and bind it to the proof. Because if we wouldn't do that, we wouldn't have it in there, then someone can just jump on the blockchain and just front run us and just change the vote. That would be possible. But the thing is, since we bind the answer of the vote, what we want to vote into the proof, nobody afterwards can change it. Yes. That's kind of the circuit, how it looked like. Maybe if somebody has a question afterwards, we can discuss it, or you can come to me. I'm the whole day here, and we can just discuss. I'm also happy to learn more about these things, but it's definitely very cool. And now we're coming to the coolest part, what I really enjoyed the most, and that is generating the Solidity Verifier Contract, because it's just magic for me, and that's pretty cool, and I think that makes it very easy to use these things, because you saw, it's just this little Rust-written program you have. In the end, you're getting a verifier contract you deploy, and you can just integrate into your smart contract. Maybe before we're doing this, I just wanted to give you a quick heads up. So if you want to do it in the CLI, we're going to CD to our circuits folder, and then we're just going to run a Nargo check. Maybe we need to do a Nargo compile before because I deleted the folder. OK, now we have a. Okay, what Nargo compiles does, it compiles the whole thing down, and we have a JSON and all about the circuit, and you can use it then for the front end to call all the libraries in there. This is another thing, but here, when you run the Nargo check, you see all the inputs you have to make in order to create your witness, and then your proof in the end. And this is exactly kind of, as you saw before, our public and private inputs in here. And when you fill these in, I mean, I don't do this now, because it's just getting complicated with the siblings, because you have to create all the different hashes, and you need to add it to it, and you need to pre-populate it up front, and so on. But this is kind of what you would do in a CLI form. So in order to try out the circuit, how it works, and then you can run against that, you can create a witness, and then out of it in the CLI, you can create a proof, and then you have just a big proof of a lot of numbers, and you could use it to do something with it. Kinda. That would be in the CLI, but the cool thing is we don't have to do that in the CLI, because we're going to do this in a second in the front end, where we're just calling the right libraries from CKKit for that. So what we would do now in order to create the Solidity contract is actually just these two commands you're going to run. So here we're going to use the Berentenberg. And we first kind of need to create a verifier key, is it called. And this is kind of the base, and then out of that, they're going to create the Solidity contract. But let's run this in a second. Hopefully this works now. Yes, and as you can see here over there, we have the verifier key. That's it. And now let's go call Berentenberg again. And we call the function write Solidity Verifier. And we're going to pass in the verifier key and where it should put the verifier contract. And as you can see, we have now a full verifier contract very easily created in here. It's a very long one. And this just gets created automatically in there. And there's only one important thing in here. That's the verify function. So we have a nice interface here, but if you look at the verify function, this is exactly what we need to call. And we can just use it as a condition in our function we want to call that in a second. And let's maybe, we have the verifier contract now. Let's jump into our contract. That's the voting.sol contract. So the register function, I won't touch further on. And then here we have the voting function. That's kind of the voting function. And here you can see this line here is where we call the verifier contract. And we're going to pass in the proof, and we're going to pass in the public inputs. So the public input is everything that has a pub keyword before, that is open, and the proof is here. And before that, you can do that. You have to, of course, define getting your public inputs and in the right format. This is always the main, or that could be some issues, how you get it from the front end then into the Solidity contract, that all the formatting is right. I was struggling there a bit with it. One very important thing, and I forgot it first, is we want to check for the root. So in the Solidity contract, whenever we're going to add with the insert function up here, insert, the root changes because it recalculates above the root, and it gets stored in the contract. And what we're going to do, the person creating the proof is calculating the proof kind of off-chain, and then asserts inside the proof also has to, like we saw, we calculate the proof and we put the proof in. But we need to make a connection to the proof in the smart contract, because if we wouldn't do that, I could just come up with a complete random tree I created off-chain and just pass it in. It will work, but it's completely disconnected from the tree. So everyone, my whole contract wouldn't work anymore, and everyone can just do whatever they want and just vote as they want. And that's a very important thing to keep in mind. Yeah, I think that's it. That's kind of the most important thing in here. I mean, you're going to check here as well. You're going to set the nullifier hash so that a person cannot vote again. So it's only one-time voting. So you want to track that. And then in the end, you just count the votes on these sites. So, are there, maybe I'm just going to make, I'm looking very confused faces, so I just want to give, are there any questions in the meantime? Anything that's unclear, confusing?
Test. Yeah. So can I get clarification on the nullifier hash? So what's to stop a voter from using a separate nullifier?
Sorry, again?
So you have the public nullifier hash, right? And then you have the voter has a private nullifier. So what's to stop a voter from using another private nullifier?
I mean, every person who is registered has with the commitment put on the Merkel tree. And the registration consists of a secret and a nullifier. So they are unique. So as a person, I'm registered having only one nullifier. All the other nullifiers won't work because I cannot come up with a random nullifier because I don't have the commitment on the chain. On the chain in the Merkel tree. Does it make sense?
Yes, I guess.
I can also later then, when you want, come to me, we can just go through and I can show you the flow inside if you want. Okay, so what another question?
Yeah, so my question would be initially... Testing, yeah. I was trying to speak loud so everyone can hear me. Yeah, so my question would be, you said initially you need to send a list of address to be whitelist in order to be included in the Merkel tree. Can be computed, figure out if they have common root. My question, if I send my address to that person to be whitelist, they already know who I am, right?
Yeah.
So in that case, realistic voting scenario, I don't want anyone to know who I am, but I still want to vote. Do you know what I mean? Like, I don't want to give someone, at least there's a single authority in this case, they know I've been whitelisted. So how prevent their reveal my identity to even that single authority to be included in the first place, if that makes sense to you?
I'm not sure if I understood it correctly. You mean that with the allow, what is kind of the benefit of the allow list?
Yeah, exactly. Yeah,
Can you do
you think allow list in that sense?
I mean, you want to kind of curate the voters. So imagine a country election, for instance. You only want to have your citizens vote. You don't want to have anyone else vote. Because, I'm from Germany, so only German citizens are allowed to vote. But if you're from the US, you're not allowed, if you don't hold a German passport. So you kind of restrict the voters in this sense. So you could have kind of different requirements for the voters coming in. And the easiest one is you have an owner of the contract, and that adds the addresses to the allow list. And these persons who are in the allow list can register themselves. With registering, putting their commitments on the chain, in the Merkel tree.
So does that mean in the case of citizenship verification, the whole Merkel tree, including the whole German population, on the whole tree, pre-whitelist in that sense?
Yes, they're pre-whitelisted. I mean, that goes a little bit further away. That's kind of use case I've thought also about. It might happen that you kind of get sending to each of every German, you would send a letter and there is a private number in it and you use that private number maybe as the registration to the contract. Kinda. But I mean, there are different ways. I mean, I can go later. The different things you could use to have people registered. You can look for balances of ERC20 token or NFTs or whatever you want in there. But the thing is, as soon as you open it up to everyone can just vote, creating addresses. You don't get the effect anymore because you can just have Sybil attack the whole thing. So you need to have some restriction for the application.
Yeah, the reason I'm confused, during the first step of verification, pre-whitelisting process, how can you avoid to be not identified? That is the kind of the confusion I have. So I'm more about the single point of failure during the initial verification of setting up the Merkel tree, if that
Maybe
makes sense.
I can show you. Let me see. I can walk you through the, if it loads. Okay, maybe. Okay, sorry for the, maybe, okay, I see I don't have so much time anymore. The thing is, like I said, there's one time you're going to create the commitment off-chain. That's just a thing. I'm just going to touch it briefly. As you see, the secret and nullifier are important because anyone who has these two can prove that they are on the Merkle tree, and then your whole privacy is gone. So you keep that on your device, and that's it. And you're going to generate this off-chain, and you only put then the hash version of these two on-chain. That's kind of the commit scheme we're having, and then. There is a proof generation. So the generating commitment is for the registration, and then when you want to vote, you need to generate the proof that you're on the Merkle tree and you're there. And I'm just going to show quickly in the Next.js to the components. Oh no, where is it? The generate proof. I mean, what we want to do, as you can see, maybe the first thing I get, we need to create the tree off-chain. So what we need to do on for the proof generation, we are just on our laptop, and we need to reconstruct now for ourselves because we know where we are and we have the inputs. We need to reconstruct the whole tree, and that's what we're going to do also with a Lean IMT, like a Lean Incremental Merkel Tree library in here. And then we're going to form all the inputs, and we're going to because we have them, the private ones, and then we're gonna let Noir use Noir. We're gonna generate the witness, and then we're gonna pass it into the Brandenburg backend, similar like I said before, and then we're gonna generate the proof. And that proof, then we're gonna pass into the voting function, the functionality. That's kind of in a nutshell. One important point I wanna mention. And sorry that I have to cut it short right now, but it's just because of time, is the separation of the addresses. Because you need another address in order to call the vote function when you have the proof. Because if you would use the exact same address again, what is the whole point of create any proof? Then we could just leave all the zero knowledge proof away. So we need a way to have a fresh address that is not linked to your address. Because even, like I started in the beginning, if you just have an address, there's your funds, you're going to generate a new address and you're going to set funds to it. Everyone who can do a little bit of chain analysis would know this account also belongs to you. So you really need a complete fresh address to vote. And therefore, I mean, if you're using local chain and Yarn, and the Yarn chain, it's very simple. You're just going to spin it up, and you just in a deploy strip, you say, okay, fund this account. But how does this work in a real world application? And the thing is that you're just gonna that you use smart account abstraction with a verifying paymaster. So you have a paymaster somewhere. You're gonna spin up completely a fresh account, and that gets then paid with a verified paymaster that belongs to the protocol, for instance. And then you have no link to that. And you don't even need to know this account, who voted then for you, because you will never use it again. Just one time created, pay the transaction fee, and then it goes in. This is also a very important point when you think about considering building these applications, that you always, for the new address, you need some way to sponsor the transaction, because you want to break this link between the sender and the receiver address. Maybe a little things I just want to elaborate on are kind of the final considerations I had with the app. I mean, I haven't touched it. The thing is, you want to have some kind of a root history array. Because imagine many people interacting with your chain, and they're going to add new commitments. Whenever they add a new commitment or get a register, there's a new Merkle root. But when you're only tracking this one, it happens many times. You generate the proof off-chain. You're going to send it to the Merkle tree. But in the meantime, someone else already added the commitment to the Merkle tree. That means a new Merkle root would have been created. And so the comparison fails. even if you have the secret everything well done, because just the Merkle root changed. And that's why a good behavior is to have an array. So you kind of having different, all that you're collecting kind of, I don't know, it depends how much you want, 10 or whatever, kind of these different roots in an array, and you're always letting drop out the oldest one, so to make it work. And another thing, what is also very important, because you need to build the whole Merkle tree yourself in the front end, you need very good indexing for that, because you need to look to all the to keep the thing running. Then, as I said, really the privacy depends on the amount of people, so you're always making sure that you're having as many people using that when you want to achieve huge privacy. Of course, it doesn't matter if you have a voting app like us and we're using it in the BuidlGuild and we have 50 people and 15 people and we just let them vote. We know that's all the voters, but the more precarious it is, or the more you want to really get the privacy on some withdrawal or whatever, then the bigger amount is good. And of course, the gas sponsorship is another point I would like to mention. That's what I said with the account abstraction. There's also a thing you need to wrap around how you're going to do that in order really to break cleanly the separation. Then another big point, I put it here, that was kind of what we're touching on, is kind of the registration strategy. Because it's also a hassle. So imagine I want to use now a hidden a voting application with you all. And I only have the allow list where I add the addresses. What I need to do now first, I need to collect each of you one address and then add it to the allow list, and then you can vote. But this is a very cumbersome process, isn't it? So, I mean, there are other ways. We could have given out to all voters some NFTs already, then I check for the NFTs, and that could be the allow list, or whatever you come up with. That's another idea you can do. And, and another limitation to the whole application is, and I mean, Vitalik has written a blog post about it, and there is a protocol out there that's kind of the Macy protocol, Macy framework or infrastructure. And what it exactly means, because in this way we constructed this challenge. You can prove in the end to anyone what I have voted on, because I have the proof. So if Austin asks me, hey Philip, I give you 10 ETH when you tell me what you have voted on, I would then give him the proof and say, yeah, I have voted yes. Where are my 10 ETHs, kinda. And the thing is, with the Macy framework, it kind of protects you because it's another third party integrated in the whole thing. I mean, that also leads to more complicated and to more trusted setup, kinda. But this will deal with the whole tally process. And in that sense, because OCK, you cannot prove what you have voted on. But on the other side, it has also a downside, because they cannot fake your vote, but they can withhold your vote then in the end. So you kind of you kind of introduce some censorship resistance again in the whole thing, what you need or want. So I think the real voting is not invented yet. There's definitely plenty of room to play around with and try out CK, because I think it has so many possibilities. And if you're thinking of, I just used now the vote function in there, but actually that's kind of the basis for everything in the voting, and you can just put whatever you want behind the dog, what people can do. Yeah. I think that's it. I mean, that's it more or less. What we have touched. We have touched the commitments, kinda how using that to bring some secrets on the blockchain. Then how we gonna build the Noir and the circuits a little bit. I didn't go too much deep into that. I thought I had more time, but that wasn't the case. Merkle proofs and Merkle trees, why they're important, and what is the difference between a normal one and the Lean Incremental Merkel Tree. And then the coolest thing, how we're getting the Solidity Verifiers out of it, and we just can use it for our smart contract. Yeah, and that's it from my side. I hope it was not too confusing. I think we still have a couple of minutes for any questions, if there are. Otherwise, like I said, I'm here the whole day. So if there is anyone wanted to discuss with me something, I'm happy to do that, because I really like the topic and I think it has so much potential. It's pretty cool. And yeah, that's it. And don't forget our speedrunners event. Yes, here's the QR code to it. Thank you. Oh, doesn't work. Okay, then sorry. Oh, there's a weird address in there. Can it work? It's an EVE address. Now, there it is. Don't even know which address that was. Now it should work. Sorry for that. Does it work?
One question. I understand Solidity smart contracts have a maximum size, right? And the contracts that Noir generates are pretty big, so I was wondering if this is something that limits the use cases of CK technology, and also if there's a way to realize beforehand if your contract is going to be too big or just going to realize when you compile it.
Yeah, I have heard that in the beginning that it's very big, and I mean I scrolled through the contract and you saw how long it is, the verifier contract. But we were deploying also, we built some voting app with the contract. It's a little bit bigger, but the circuits stay the same. It was no issue and not so expensive to put that on base. I haven't done it with mainnet. That probably could be a different story, but on base it was no issue to deploy the smart contract.
Thank you. Hi, Philip. I only want to add something to his question. Maybe you can check. Gracias. Maybe you can check Semaphore. Semaphore allows you to hide the identity of the people inside the voting group, and you can combine with this example. Semaphore, I can share you the link. And what Semaphore does, it hashes the identity. You can use a sign, affirm from your wallet. You can use a secret word. You can use a hash that you hold on a specific NFT or on a specific token, and then use that. The tricky part is how you design the mechanism to detect what kind of variables are you using into the entry group. But yeah, it's from PSC.
Thank you.
Hello. Well, thank you very much for your talk, first of all. Then I don't know if my question is kind of basic, but can you simply track? I don't know if you can see on real time how the voting advances. If you see there's a registration, of course, of every movement, if an address votes for something, and then you see like the pool moving forward, if you can somehow end that like linking.
Sorry, can you speak a little bit louder?
Yeah, sorry. So isn't there a way in which I could link if I see a transaction registering from an address that it's voting, and then I see like the vote pool somehow moving? Isn't there, like, couldn't I simply like track or trace back to which is the address that actually voted?
Yeah, that's a very good point, actually. And yeah, when we did, we built a kind of a more productive app. It's kind of hidden vote. We started to build out, and there we integrated a registration period. So before you can vote, I mean, I haven't even shown now the app because you have a registration period, because exactly what you said, you don't want to allow that someone registers and immediately vote, because this causality you can just link, and then you know exactly that person might be exactly that voter. Yeah, that's why if you want to host a vote, for instance, you can say, okay, the voting period, the registration period is open for 1 week. Everyone registers, and then you open it up afterwards, and then let the people vote. And then you don't have this issue anymore, because you don't know who then voted and which could relate to which address. Okay, thank you very much.